Hi, I'm Ezra, a third-year BSCAM student from the Polytechnic University of the Philippines, and today I will be doing a presentation on one of the theories associated with explaining the behavior and formation of chemical bonding. Today I will be discussing VBT, or the valence bond theory, as one of the two basic theories associated with explaining the formation of chemical bonding through quantum mechanics along with MOT. So, VBT basically says that a covalent bond will be formed when an overlap happened between the half-filled valence orbitals of the present atoms. So, the electrons involved in this bonding process are of course the valence electrons. So, quick recall, the valence electrons are the electrons located on the outermost shell of an atom, and these are the ones usually active in the formation of chemical bonds. So again, bonding in VBT is described as the overlap of these atomic orbitals, and in the overlapping space of these orbitals, the probability of finding a pair of electron would be greater. On the features of VBT, or valence bond theory, as a covalent bond is formed from the overlap of these half-filled valence orbitals, it will then result into an overlapping orbital, and in this overlapping orbital, the two electrons that occupies it or is located in it would always have different or opposite spins. Next feature would be that the greater the extent of the overlap between these orbitals, the greater the strength of the bond formed. Therefore, the lower the extent of the overlap, the lower the strength of the bond formed. And last feature would be that each atomic orbitals has a specific direction, except of course for a s orbital because it is spherical in shape. Each atomic orbital has a specific direction, hence the atomic overlap between these orbitals would take place in the direction wherein it is maximized. Presented on the screen is an example of hydrogen atoms overlapping. So of course, hydrogen atoms has a valence electron of 1 from its configuration 1s1. So on the upper right side of the slide, you can see that as the orbitals of these two separate H atoms overlap, it's similarly combined into another oblong-shaped-like figure, which of course represents the formation of the covalent bond and the new molecule H2 or H2 gas. Below it, you can see that a red gradient is found in the region of this overlap, and this red region is the electron density, and it tells us that the probability of finding an electron in it is great. Next, I would be talking about two types of characterization of overlaps formed from atomic orbitals between atoms, and these are called the sigma and the pi bonds. The sigma bond is a bond or an atomic orbital formed in the internuclear axis. The internuclear axis is the region or space in between the nuclei of the atoms forming a bond. The electron density is then found directly in this internuclear region or internuclear axis. And the sigma bond is symmetric with respect to 180 degrees rotation about the formed bond. On the other hand, pi bonds are bonds or orbital overlap formed between two unhybridized p orbitals. The electron density is found in the region of space above or below the nuclei, as contrast to the sigma bond where the electron density is located in between the nuclei of the atoms forming the bond. So to better visualize how the pi bonds are formed, let us refer to the image on the upper right, wherein two unhybridized p orbitals overlap to form a bean-like shaped figure next to it. So Pi bonds are also asymmetric with respect to a 180 degrees rotation to the bond form. This slide presents another view of the positioning of the unhybridized p orbitals and why pi bonds are formed sideways. So as you can see, if we were to have two of these atoms overlap, the sp orbitals would be the one forming the sigma bond on the internuclear axis, while the unhybridized p orbital would then be forming a sideways overlap with each other. So therefore, the electron density formed will be on opposite sides of the internuclear axis. In this slide, we analyze which would be stronger, a pi bond or a sigma bond. So let's recall, a sigma bond is formed from the orbital overlaps located in the internuclear axis, while pi bonds are formed from unhybridized p orbitals perpendicular to the internuclear axis. So we can compare that the sigma bond has a more effective orbital overlap because the extent of its overlap is greater as compared to the pi bond, which has a perpendicular orbital overlap. Therefore, as we remember from the features of valence bond theory, a stronger or a larger extent of orbital overlap results to a stronger bond. So therefore, a sigma bond is a stronger bond or the stronger bond. This slide shows us what kind of bond does a single, double, or triple bond has based on its atomic orbital overlaps. So we can refer to the image on the right. A single bond is made up of only one sigma bond. A double bond is made up of one sigma and one pi bond, while a triple bond is made up of one sigma and two pi bonds. Next, we talk about homonuclear diatomic molecules. So homonuclear diatomic molecules are simply molecules made up of two atoms from the same elements. So examples would be hydrogen gas, fluorine gas, oxygen gas, or nitrogen gas. So in the next slide, we would see how all these diatomic molecules are expressed or shown in their atomic orbital overlaps. For hydrogen gas and fluorine gas, we observe a formation of a sigma bond. For oxygen gas, we observe formation of a sigma and a pi bond, while in nitrogen gas, we observe the formation of a sigma and two pi bonds. Last, we talk about polyatomic molecules. So polyatomic molecules are made up of different atoms covalently bonded to each other. So on the right, we see an example of an s orbital of a hydrogen atom and a p orbital of an f fluorine atom covalently bonded to each other, forming a polyatomic molecule, hydrofluoric acid.
So our next topic is hybridization. It is proposed by Linus Pauling, and he states that the valence electron orbitals of isolated or individual atoms are different from those that are bonded in a polyatomic molecule. It is greatly used in the observation of bondings between polyatomic molecules or molecules that had a different set of atoms. This hybridization is a process of mixing orbitals with a comparable energy from one another to produce a hybrid of these orbitals with the same energy. Take note that hybridized orbitals has definite symmetry and orientation in space. These orbitals are positioned as far away from one another in order to minimize the effect of repulsion. This is called the valence shell electron pair repulsion theory. So the first kind of hybridization that we will tackle is the sp hybridization, and we will take beryllium chloride as our example. So see here that beryllium is our central atom, and we will focus on the valence electrons of beryllium in this molecule. So we can see in the ground state of beryllium that it has a paired valence electron in its 2s2 orbital. But in order to form a covalent bond with chlorine, it needs two unpaired electrons. So what will happen here is that the electron of beryllium in the 2s orbital will be excited or promoted into the 2p orbital, and we will produce our excited state. So this excited state has one unpaired valence electron in the 2s orbital and another unpaired electron in the 2p orbital. These two unpaired electrons now can undergo hybridization in order to produce two hybridized sp orbitals with two unpaired electrons. So this new 2sp hybridized orbitals of beryllium will then overlap with the 3pz unpaired valence electron of chlorine in order to form a sigma bond or a covalent bond with one another and form a linear geometry. So another kind of hybridization that we will tackle will be the sp2 hybridization, and we will take boron trifluoride as our example. Just like beryllium chloride, we will take boron as our central atom. So we can see in its ground state that boron has a set of paired valence electron in its 2s orbital and one unpaired valence electron in the 2p orbital. But in order to form covalent bond with fluorine atoms, it must have three unpaired valence electrons. So what will happen here again? We will take the paired electron of boron into the excited state. So we will have three unpaired electrons, one in the 2s orbital and another two in the 2p orbital. This three unpaired valence electron will undergo hybridization, particularly the sp2 hybridization, and we will produce three unpaired valence electron in the sp2 orbital. These new sp2 hybridized orbitals of boron can now overlap with the orbitals of fluorine and can form a sigma bond with one another or a covalent bond, and will assume the trigonal planar geometry. The third kind of hybridization that we will tackle is the sp3 hybridization, and we will take methane as our example. Carbon here is our central atom, and we will observe its ground state. So we can see here in carbon's ground state is that it has one paired valence electron in the 2s2 orbital and two unpaired valence electron in the 2p orbital. But in order to form methane, it must have four valence electron in order to form a sigma bond with hydrogen atoms. So what will happen here, just like the previous hybridization, we will excite the valence electrons of carbon, and we will have our excited state, which has one unpaired electron in the 2s orbital and three unpaired electrons in the 2p orbital. So these four unpaired valence electrons will now undergo hybridization, particularly the sp3 hybridization, and produce four unpaired electrons in its sp3 orbitals. So this new form of four sp3 hybridized orbitals in carbon will now overlap with the 1s orbitals of hydrogen and will form four CH sigma bonds and will now covalently bond with each other in order to form CH4 or methane with a molecular geometry of tetrahedral. The next type of hybridization that we will tackle in this video is the sp3d hybridization, and we will take phosphorus pentachloride as our example. Phosphorus here is our central atom. So we will look at the ground state of phosphorus and see that it has a paired electron in its 3s orbital and 3 unpaired electrons in its 3p orbital. So what we're gonna do is again excite this paired electrons in order to produce the excited state so that it can form sigma bonds with 5 chlorine atoms. So in the excited state, we will have 1 valence electron in the 3s orbital, 3 valence electron in the 3p orbital, and 1 valence electron in the 3d orbital. These 5 orbitals, these 5 unpaired electrons rather, will undergo hybridization and form 5 sp3d orbitals. These new 5 sp3d hybridized orbitals of phosphorus will now overlap with the 3 pz orbitals of the 5 chlorine atoms that will be covalently attached through sigma bonds in the phosphorus. This type of atom, this phosphorus pentachloride, will take form the geometry of trigonal bipyramidal. So far, we have tackled different hybridization in polyatomic molecules, and mostly we have discussed about sigma bonds or single bonds in these polyatomic molecules. So the next thing that we will discuss further will be the formation of pi bonds or the double bond and triple bond in our polyatomic molecules. For the double bond, we will take ethene as our example. So in ethene, we have 2 carbon atoms and 4 hydrogen atoms. We will take carbon as our central atom. I mentioned that we have 2 carbon atoms, but for the hybridization, we will focus on only 1 carbon atom and discuss its ground state, excited states, and its hybridized state. So for the ground state of carbon atom, as mentioned earlier, it has 1 paired valence electron in the 2s orbital and 2 unpaired valence electron in the 2p orbital. So what will happen here is that we will excite valence electron so that it has 4 unpaired valence electron, 1 in the 2s orbital and 3 in the 2p orbital. However, for ethene, our hybridization will not be sp3. Why? Because we only need 3 hybridization states so that carbon will link to 2 hydrogen atoms or form 2 CH bonds and 1 carbon-carbon bond. So we only need 3 hybridization states. The 1 unpaired electron in the 2pz orbital will remain the same. So for this, after the carbon atom formed 3 hybridized state of sp2 and 1 unpaired electrons in the 2pz, these hybridized orbitals will then overlap with the 1s orbital of hydrogen and form a sigma bond, and the other sp2 hybridized orbital of carbon will overlap with one another in order to form carbon-carbon bonds. Now, what happens to the 2pz unpaired valence electron? This 2pz unpaired valence electron will overlap sideways and interact with one another in order to form the pi bond. This pi bond will then be our double bond. So now we can have our ethene, which has a carbon attached to 2 hydrogen atoms and a double bond on the carbon-carbon atoms. So we have discussed the double bond formation in ethene, and now we will discuss the triple bond formation in ethine. So in ethine, we have 2 hydrogen atoms and 2 carbon atoms attached together. So what will happen here is, again, we have the ground state of carbon atoms with 2 paired electrons in the 2s orbital and 2 another unpaired electrons in the 2p orbital. So we will excite this valence electron again and then form 1 unpaired electron in the 2s orbital and 3 unpaired electrons in the 2p orbital. And just like what happened to ethene, we will not use all of this unpaired valence electron in hybridization. And in the case of in ethine, we will only use 2 hybridized state because carbon here will only attach itself or form sigma bonds with hydrogen and carbon-carbon atoms. So we will have 2 sp hybridized state and the 2py and 2pz valence electrons will remain in the unhybridized state. So after this 2 hybridized state of carbon, it will now form sigma bonds with the 1s orbital of hydrogen and another sp hybridized overlapping with the sp hybridized of carbon of another molecule of carbon, which will form the carbon-carbon bond. So after this, the other 2 unpaired electrons of each carbon will interact or overlap with each other sideways and will form the 2 pi bonds. So we will now have sigma bonds with the hydrogen atoms, sigma bonds with the carbon-carbon atoms, and then another 2 pi bonds from the 2py and 2pz unhybridized valence electron. And that will cause our triple bond. So now we will discuss the geometry of these polyatomic molecules. Remember that I said earlier that hybridized orbitals has definite symmetry and orientation in space. They are positioned as far away from one another in order to minimize the effect of repulsion. And this statement is called the valence shell electron pair repulsion theory. And this causes the atomic orbitals to position themselves in a geometry. And this is what we're going to tackle next. So now if we have a polyatomic molecules that has 2 electron dense areas, it will have a geometry of linear. So its only geometry, the only geometry that it will assume will be linear and no other. And it has a bond angle of a 180 degrees as it is linear. If we have a 3 electron dense areas in a polyatomic molecule, it will assume a trigonal planar or bent geometry. If it does not have a lone pair, it will assume the trigonal planar geometry. And if it has a 1 lone pair, as you can see in the table, it will assume the bent geometry. This kind of geometry will have a bond angle of 120 degrees. The next one is the polyatomic molecule with a 4 electron dense areas like we have seen in methane. And this will assume tetrahedral, trigonal pyramidal, or bent geometry. If it does not have a lone pair, it will assume the tetrahedral geometry. If it has 1 lone pair, it will assume the trigonal pyramidal geometry. And if it has 2 lone pairs, it will assume the bent geometry. This tetrahedral geometry will have a bond angle of 109.5 degrees. And if it has lone pairs, it will be less than but nearly 109.5 degrees also. So for another is the 5 electron dense areas. This will assume a trigonal bipyramidal electron pair geometry if it does not have a lone pair. And the Sohor's T-shape and linear geometry if it has 1, 2, or 3 lone pairs respectively. Last but not the least is the polyatomic molecules with 6 electron-dense areas, and it will assume the octahedral geometry if it does not have lone pair, and it will have the square pyramidal, square planar, T-shape, and linear geometry if it has a 1, 2, 3, and 4 lone pairs respectively. Please take note that for the geometry of trigonal bipyramidal, the bond angle between equatorial orbitals are 120 degrees away from each other, while the bond angle between the axial and equatorial orbitals are 90 degrees, except of course for the 6 dense electron areas of a molecular geometry with 3 lone pairs. It will assume the linear geometry in which that has a bond angle of 180 degrees. For the octahedral geometry, the equatorial orbitals have bond angles of 90 degrees, as well as the axial equatorial orbitals has bond angle of 90 degrees also. And again, except for the molecular geometry with the 4 lone pairs that will assume a linear geometry and have a 180 degrees bond angle. So that's all for our valence bond theory. Thank you for listening.